Imagine it's 1983. You're a programmer, one of the architects of the new digital world. You've just spent 7 days writing a brilliant piece of code, not on a sleek laptop, but by punching 200 or more of tiny, precise holes into a stack of manila cards. Your program is a physical artifact. You walk your stack of cards down the hall to the computer room, hand them to an operator in a white coat, and then you wait. You wait for hours, maybe even a day. The next morning, you get a printout. It's not your program running beautifully, it's a single cryptic line, execution failure. Somewhere in one of those hundreds of cards, you missed a single comma, and your feedback loop, the time between your idea and knowing if it worked, was 24 hours long. Now, fast forward to today. You're typing into a code editor, and before your finger has even left the key, a red squiggly line appears under your mistake. The feedback loop isn't a day, it's not a minute, it's less than 100 milliseconds. It's faster than your own perception. That gap, from a full day to the blink of an eye, isn't just a story about technology getting faster. It's the story of how our relationship with machines has fundamentally changed. It's the story of how we learned to talk to computers, and it's the story we're going to unravel today. Hello and welcome to Mindcast. I'm your host, Will. In each episode, we try to look at the hidden systems and mental models that shape our world. And today, we're diving into one of the most important yet invisible revolutions of the past 50 years, the evolution of software development. Now, I know what you might be thinking. Coding? Isn't that for super geniuses and hoodies? And yes, it can be incredibly complex, but the story of how we program computers is really a story about us. It's about how we manage complexity, how we offload tedious work from our brains, and how we turn abstract ideas into functional reality. My promise to you in this episode is this: by understanding the 4 major eras of how humans have instructed machines, you won't just understand the past, you'll get a crystal clear vision of the future of our partnership with technology, especially with the rise of artificial intelligence. This journey will take us from physical punishment to digital conversation. So let's start with that first era, the one I described in the opening. We'll call it the bare metal paradigm. This was the world from the 1970s into the 80s. The name says it all. You were programming as close to the physical hardware, the bare metal of the machine, as you could get. The document that inspired this episode calls the developer from this era the human compiler. Think about what that means. A compiler is a program that translates human-readable code into the ones and zeros the machine understands. In this era, the developer had to do most of that translation in their own head. They weren't just thinking about the logic of their program, they were manually managing memory addresses, thinking about the physical limitations of the computer's registers, and writing in a language called assembly, which is just one step removed from the raw binary code the machine speaks. Imagine trying to write a book, but instead of writing sentences, you have to provide the exact dictionary page number and line number for every single word you want to use. The cognitive load was immense. A single misplaced space or comma wasn't a typo. It was a catastrophic failure that you wouldn't discover for hours. The friction between idea and execution was brutal. This was a world of physical punishment for mental errors. The computer room itself was a kind of temple, a climate-controlled, sealed-off environment. The machine was the scarce resource, and human time was considered expendable in comparison. This power dynamic, where the human served the machine's needs, defined the entire era. Then, something revolutionary happened. It wasn't a faster computer, it was the screen, the video display terminal. This kicked off the second paradigm, which we can call the lexical screen. This is the era of the 80s and 90s. The punch cards were gone. Now, developers could type their code into a text editor on a screen, a glass teletype, as it was called. The analogy shifts from chiseling stone to using a basic word processor. You can see your words.
You can use backspace. This alone cut the feedback loop from days to minutes. You could write some code, run the compiler, and see the errors almost immediately.
But the real breakthrough of this era was a concept called syntax highlighting. Before screens, some programmers used a clever hack, color line printers. They would print their code so that commands were in black, variables in green, and comments in red. It didn't change what the code did, but it gave the human reader visual cues to see the structure. It was the first sign that we realized code is read by humans far more often than it's read by machines. Syntax highlighting took that idea and put it on the screen in real time. As you typed, your text editor would color code the words. To a non-programmer, this might seem like a small aesthetic touch, but neurologically, it was a revolution. Think of it this way. The editor didn't understand the meaning of your code, but it understood the categories of words. It knew what a verb looked like, what a noun looked like. If you accidentally typed a noun where a verb should be, the color would be wrong. Your peripheral vision could catch the error instantly, freeing up your conscious mind to focus on the hard part, the actual logic. This newfound power led to the legendary editor wars of the late 80s and 90s. On one side, you had users of an editor called Emacs, which was infinitely customizable and powerful. On the other, you had users of VI, or its successor Vim, which was incredibly efficient, built around modal editing and lightning-fast keystrokes. This wasn't just a technical debate, it was a cultural one. It showed that developers were no longer just battling the machine, they were actively optimizing their own minds, shaping their tools to minimize cognitive friction. The developer's role shifted from a human compiler to a logic typist. They were still manually writing out every instruction, but the tool was now helping them see the basic structure of their language, reducing friction and cognitive load immensely. It was a huge step forward. But the computer was still just a passive canvas. It was a colorful but ultimately silent partner. That was about to change. This brings us to our second key insight and the third paradigm of programming, the era of the IDE, or Integrated Development Environment, which dominated from the late 90s all the way to the 2020s. This is where the computer stops being a passive canvas and becomes an active, all-seeing grammarian. The central metaphor for this era is an experience we've all had, the red squiggly line. We see it in Microsoft Word or Google Docs when we have a typo or a grammatical error. This feature found its most powerful expression in the world of programming. What was happening here was a profound technical leap. As a developer typed, the IDE was no longer just matching patterns to colorize words. It was running a lightweight version of a full compiler in the background in real time. It was constantly analyzing the code and building what's called an abstract syntax tree, or AST. Let's use our book writing analogy again. In the first era, you were chiseling in stone. In the second, you had a word processor that could color code your parts of speech. In this third era, your word processor isn't just color coding. It's building a live, interactive sentence diagram of your entire novel. It knows every character, every plot point, every relationship. It understands the deep grammar of your story. This systemic awareness gave birth to one of the most powerful tools in a programmer's arsenal, intelligent code completion, famously branded as IntelliSense by Microsoft. This wasn't just predicting the next word. This was like having a librarian who, the moment you typed a character's name, would instantly present you with a list of all their known associates, their past actions, and the objects they might interact with. It was a monumental offloading of cognitive work. Developers no longer had to memorize thousands of commands across dozens of libraries. The IDE knew the library, and it presented the developer with only the valid, contextually aware options. Because it has this deep understanding, it can do incredible things. It can auto-complete your sentences because it knows what words make grammatical sense in that context. It can let you click on a character's name in Chapter 20 and instantly see where they were first introduced in Chapter 1. And of course, it can give you that red squiggly line.
That red line meant the feedback loop had shrunk from minutes to milliseconds. The computer was now a tireless proofreader, checking every single character you typed against the strict rules of the language. The developer persona evolved from logic typist to structural engineer. They were now focused on a higher level of abstraction, connecting larger components together, confident that the IDE would catch the small mechanical mistakes. But this system, as powerful as it was, had an Achilles heel. It was entirely deterministic. It was based on a rigid, unbending set of rules. And as software projects grew into colossal, sprawling systems with millions of lines of code, this rigidity began to break down. Developers started experiencing a phenomenon they called the false red squiggle. The IDE would cover their screen in red lines, signaling catastrophic project-breaking errors, but the code was actually fine. The background compiler had simply gotten lost. Its internal map, the AST, had become corrupted or desynchronized from reality. The tool designed to reduce stress was now a new source of anxiety. You had to start debugging the debugger. The all-seeing grammarian was like an obsessive editor who was brilliant at rules but had no sense of nuance. It could tell you that you missed a comma, but it couldn't tell you if your paragraph was boring, if your logic was inefficient, or if your entire premise was flawed. It understood the syntax perfectly, but it had zero understanding of your intent. And it was this limitation that set the stage for the most dramatic shift of all.
And that brings us to our third key insight and the fourth paradigm, the paradigm we are living in right now, the era of artificial intelligence. This is the moment the computer transforms from a critic into a collaborator. The core change is a move away from deterministic, rule-based systems to probabilistic, intent-based ones. The old IDE worked like a calculator. It knew the rules of math, and if you typed 2 plus 2, it would tell you 4. It could only operate on predefined rules. An AI-powered tool works differently. It has been trained on billions of lines of code from across the world, a dataset so vast it mirrors the data-intensive science that computer scientist Jim Gray first called the fourth paradigm. It doesn't just know the rules, it has developed a statistical intuition for how code is supposed to work. It can infer intent.
Let's go back to our writer one last time. The red squiggly line was the grammarian who said, "This is a sentence fragment." The new AI collaborator reads your paragraph, a paragraph that is perfectly grammatically correct, and says, "I see you're trying to build suspense here. The pacing feels a little slow. What if you rephrased this to be more active? Or perhaps you could generate 3 alternative versions for me to choose from." This is a complete game changer. The feedback loop has gone beyond real time. It's now a continuous, creative conversation. The scope of interaction explodes. A developer can now write a single line of instruction in plain English as a comment, like connect to the database and retrieve the last 10 user orders, and the AI can generate the entire fully functional block of code to do it. It can translate code from an ancient language to a modern one, solving the exact kind of legacy migration problems that were so painful in the first and second paradigms. It can even explain complex code to a new team member, acting as an infinitely patient tutor. A developer can highlight a block of code and ask the AI, "Is this the most efficient way to do this? Are there any security vulnerabilities I'm not seeing? Can you write some tests to prove this works?" The interaction moves from the purely syntactic, "Is this code legal?" to the semantic and architectural, "Is this code optimal, maintainable, and aligned with my ultimate goal?" And this elevates the human role more profoundly than any previous shift. The physical act of typing code, of writing out the boilerplate and the mundane logic, is increasingly being abstracted away. The developer is no longer a human compiler, a logic typist, or even a structural engineer. They are becoming a system orchestrator. Their primary skill is no longer the rote memorization of complex commands and syntax. Their value lies in high-level system design, in rigorous validation of the AI's output, in curating the right context, and in asking the right questions. The human provides the vision,
the architectural blueprint, and the critical judgment. The AI acts as a tireless, brilliant partner, handling the implementation details. It's a true collaboration. So, as we bring this journey to a close, what can we take away from this four-stage evolution? I believe there are three crucial lessons. First, the entire history of programming is a relentless quest to shorten the feedback loop between an idea and its execution. We went from waiting days for a single line of feedback to having a continuous creative dialogue with our tools. This drive for immediacy is a fundamental human impulse, and it's what pushes technology forward. Second, progress is always about abstraction. Each paradigm gave us tools to handle more of the tedious, low-level details so we could focus on bigger, more interesting problems. We went from worrying about memory registers to syntax highlighting, then to automated grammar checking, and now to automated logic generation. We are always building on the shoulders of the tools that came before. And finally, and I think this is the most important takeaway for all of us, the future of our relationship with technology is collaborative, not adversarial. The rise of AI doesn't make human skills obsolete, it reframes them. The most valuable human skill is shifting away from memorization and mechanical execution and toward vision, orchestration, and critical judgment. The goal isn't to be faster than the machine, it's to have a better vision for what the machine should do. We've journeyed from the human compiler of the bare metal era to the logic typist on the lexical screen, to the structural engineer in the modern IDE, and finally to the system orchestrator in today's world of AI collaboration. It's a powerful narrative of how we offload cognition, not to become dumber, but to free ourselves to think on grander and grander scales. Thank you for joining me on this deep dive. If you enjoyed this exploration, please consider subscribing to Mindcast wherever you get your podcasts. It helps us reach more curious minds. I'm Will, and this has been Mindcast. I'll see you next time.